Hello, welcome to another module in this massive open online course. So let us continue our discussion on optimal estimation, and let us look at another interesting extension of this, and this is to the concept of what we call as self prediction, or what essentially auto regression. All right. So I am going to explain more about this. What we want to talk about is essentially the concept of auto regression. As you are familiar, regression essentially is prediction. So auto regression, auto is essentially self, prediction using the quantities, in fact the past values of the quantities, as we are going to. So this is auto means the self itself, and regression is essentially prediction or approximation. All right. And this belongs to an important class of techniques, that is essentially your linear prediction, right. So this essentially is based on the theory of linear prediction or linear estimation, which is essentially also used in linear predictive coding, which is again used in speech processing and so on. So there are many applications for this. Speech processing is also used in, for instance, compression, so on and so forth. So what is auto regression? As I have already said, auto regression is essentially the regression formed from the past sample. Of same process, and where you see this most often is in the context of a time series, that is data gathered sequentially in time. The linear prediction is best suited for a time series or the analysis of a time series. So auto regression what we call as AR, right, auto regression. This is best suited for time series analysis. And what is time series? This time series is nothing but data gathered sequentially in time, right. So time series is basically data that is gathered sequentially in time. For instance, you have the data, right, x0, x1, xn, so on and so forth. So this forms your time series. And this is your time index. And this, for instance, this n this is essentially the time index. Okay. And so, you have time series, and essentially regression that is formed using the past samples of this time series, right, that is essentially autoregression, that is prediction using the past samples. Where is this useful? Now this time series typically occurs many places, such as for instance you have some quantity that is varying with respect to time, and this is your x of n, and this can arise for instance in your stock price or the amount of rainfall or your parameters such as temperature, etc. So, these, that is when you measure these things, that is a stock price day after day, right. When you tabulate the stock prices, list the stock prices day after day as a series, day 0, day 1, day 2, so on. So, that becomes a time series. Similarly, the amount of rainfall, the temperature on a particular day. So, it occurs very, very frequently, that is wherever you are taking samples of a quantity in time. Okay. And naturally, the question that we are interested in is at this point, if you are at this is the current point, how to predict the future values of the time series. The point is you might have already guessed, the best prediction of the future can be obtained using the past samples or the immediate past samples, right, and that is essentially what we would like to regress on, that is regress on the past samples, and that makes it the autoregression, right. So, the best prediction can be obtained using past samples. This implies autoregression. So, what is autoregression? Autoregression is essentially you form the prediction, that is x hat n, using the past samples, regress based on past samples of the same process. Right. So, this is, if you look at this, what we are doing is we are regressing using the past samples of the same process, and we form the best estimate of x n. Obtain the best estimate of x n, and this is essentially your autoregressive model. And in fact, you are using L past samples, right. So, remember this implies this becomes Lth order. So, this becomes an Lth order AR model, right. If you are using one past sample like x n a1 times x n minus 1, that is a first order model, a1 x n minus 1 plus a2 x n minus 2, that becomes a second order AR model. using L pass samples, that is a Lth order AR model. Okay. Now, the idea here is what are the regression coefficients, how to determine which are essentially nothing but the regression coefficients, and these, as we know, can be determined using the LMMSE. We once again come back to the LMMSE principle, that is, if we call the quantity to be predicted as xn and then we denote by x bar, this is the quantity to be estimated. And x bar, these are the known, this is x n minus 1, x n minus 2, so on, x n minus L. Then the optimal regressor, as we know, is given as A bar transpose. This is the cross covariance of x n bar x. So, this is the cross covariance times R x bar inverse. This is your optimal regressor, right. This is the best regressor that minimizes the mean squared error, right. This minimizes the MSE, and we know that from the LMMSE principle, right. So, that is, if you want to predict or if you want to estimate x bar, then the optimal regressor is R x y R y y inverse, right. And this is basically guaranteed by the LMMSE principle. Now, let us look at these quantities. The question that we want to ask is what are these quantities R x and x bar, and what are these quantities R x bar, and for that we will need some property on this time series x0 x1 x n plus 1 so on. We will assume that this is what is known as a WSS, that is wide this is a wide sense stationary time series, that is, we will assume this is a wide sense stationary time series, which essentially implies that if you look at the correlation, that is x of n minus I times x of n minus j, this only depends on I minus j, that is the lag between these two samples. This is an important property of White's and stationary time series. That is, if you look at the autocorrelation between two different samples, x of n minus I into x of j, or you can also write it as x of I times, probably it is better to write it this way, x of I times x of j. This is simply x of I minus j, depends only on the lag, right. On the time difference. Depends only on the time difference between those two samples. That is, if we look at two samples, x of n and x of m, ask what is the correlation. The correlation is Rxx n minus m. It does not depend on n and m, but only rather the difference n minus m. Alright. So, this is essentially a very important property, a characteristic, very important property of WSS. Very important property of White's and stationary random process. Now, let us ask the question, what is R x bar x bar? This is essentially expected value of x bar transpose, which is expected value of x 0, x 1 up to x n minus 1 times I am sorry, this has to be x n minus 1, x n minus 2, x n minus L times the transpose x n minus 1, x n minus L. Now, if you expand this and write it, you will realize that this becomes expected value of, for instance, here you will have x square n minus 1, x square n minus 2, x n minus 1, x n minus 2, x n minus 1 into x n minus 2, and so on. And interestingly, if you look at it, you will see all the diagonals, expected value of x square n minus 1, x square n minus 2, expected value of x square n minus 1. Expected value is Rxx 0, because the time difference is 0, x n minus 1 into x n minus 1. Similarly, expected value of x square n minus 2, expected value will once again be Rxx 0. Expected value of x n minus 1 into x n minus 2, time difference is 1, therefore, expected value will be Rxx 1. So, if you look at it, all the diagonals will have similar elements, right. The main diagonal will be Rxx 0, the diagonal with offset of 1 will be Rxx 1, diagonal with offset of 2 will be Rxx 2, and so on. So, for instance, if you take the expected operator inside and write this, expected value of this and this, right. If you look at the expected value of these quantities, and if you look at the expected value of these quantities, for instance, right, if you look at the expected value of these quantities, expected value equals Rxx 1. Similarly, here the expected value of this quantity equals Rx1. So, if you look at this, because of the White's and stationary nature of the random process, Rx bar x bar will look like all the diagonals will be Rxx0, Rxx0, and the one offset will be Rxx1, Rxx1, and this will be Rxx1, and this will be Rxx2, Rxx2, so on. This will be Rxx of, if I am not mistaken, this will be Rxx of L minus 1, so on. So, this will be Rxx of 0, this will be Rxx of L minus 1, and if you look at this, right, all the diagonal entries, right, if you look at this, if you look at this, so if you look at this, all the diagonal, principal diagonal, right, so all the principal diagonal entries all at offset of 1, diagonal offset of 1, these are Rxx1 and 0. So, this has a banded structure, right. So, you will have the diagonal is Rxx 0, then the diagonals with are offset, the sub diagonals you can say which are offset of 1, sub and super diagonals which are offset of 1, they have Rxx1, the diagonals that are offset of 2 from the main diagonal, they are Rxx2, and so on. And this matrix, this is a very interesting structure, such a matrix is known as a Toplets matrix. So, this matrix is known as a Toplets. So, if you look at x expected value of x bar Hermitian, this has a Toplet matrix, each diagonal, principal and sub diagonals, right, diagonals are constant. Right, the diagonals are essentially constant, that is, if you look at any diagonal, all the values on the diagonal are the same. Okay. And now we want to find this, the other matrix, that is Rxn x bar, that is expected value of Xn x bar transpose which is expected value of x n x n minus 1, so on up to x n minus L, and this is equal to your, basically your you can see this is essentially your Rxx1, Rxx2, Rxxl, which implies that your A bar transpose, this is your A bar transpose is R x n x bar times R x bar inverse, which is essentially R x x 1 R x x 2 R x x L times inverse of this autocorrelation matrix, which is R x x 0, all the diagonals are R x x 0, R x x 1, R x x 1, R x x 0, R x x 1, R x x 2, so on, and then you have the inverse of this matrix. Okay. So, this is essentially your optimal self regressor. Optimal self regression, or basically your auto-regression coefficients, which minimize the mean square error, right. So, these are the best regression coefficients which can minimize the mean square error, hence can be used for your prediction, essentially also your forecasting, right. In a stock market kind of application, you would like to forecast the stock price in the next day or the next couple of days and so on, and thereby bet appropriately or thereby invest appropriately, right. So, this is a lot of applications. In fact, even coding compression, if you can predict the next values of the signal, then the remnant, what is the difference between the prediction and the actual signal, this is what is known as the innovation, and then one can actually compress only the innovation. So, there are many applications actually. Okay. And the prediction error, now one can ask the question, as a scientist, it is not just enough to come up with a prediction, but it is also important, remember, to characterize the prediction error, because what determines the quality of the prediction is the prediction error, because anyone can come up with a predictor. Now, what determines the quality of the predictor is the prediction error. So, therefore, you cannot just simply give a predictor, but also the predictor, and that is the regressor, and what is the regression error going to be, because that determines the quality, and hence that will in turn determine whether this quality or this level or this regressor is acceptable or not, because without that one is totally in the dark about what is the nature or what is the quality of the prediction. Okay. So, that is an important. So, this determines the quality of the regression. And thanks to the LMMSE principle, we already know that is your error sigma square. This is in this case, because this is a scalar quantity. So, the prediction, the covariance itself will be the variance. So, this will be R x n minus R x n x bar R x bar inverse R x bar times R x bar x n. Now, R x n this is R x x 0 minus R x n x bar. Now, this quantity, if you look at this R x n x bar inverse, this is nothing but A bar transpose. So, this is A bar transpose R x bar x n, that is expected value of x bar, this is R x x 0 minus A bar transpose expected value of x bar into x n, this is R x x 0 R x x 1 R x x, sorry, this is R x x 1, because this first value is x minus 1, R x x 2, so on R x x L, and therefore, this is essentially given as sigma e square regression error is r x x 0 minus a 1 r x x 1 minus a 2 r x x 2 minus so on minus a l r x x l. And therefore, that completes our auto regression. Now, let us look at a simple example to understand this as usual, because when we do simple examples we tend to understand things better. So, always support or enhance your understanding. We are trying to work out a simple example, right, that always helps in significantly improving your understanding, right. So, let us look at a first order AR model, that is simplest. Consider a first order AR model. Although simple, this is used very frequently. This is simply termed as AR1, that is AR subscript 1 model, okay. And of course, AR model of order n you can denote using ARn, okay. So, AR1 model, which means you are trying to form the prediction x hat of n equals beta times x n minus 1. What is beta? And the answer to that is beta equals your, well, r x n minus 1 times, all these quantities are scalar. So, I am simply using scalar quantities, not using matrices to represent these, r x n minus 1 inverse, which is r x x. Remember, it depends only on lag, r x x 1 times r x x 0 inverse, which is nothing but r x x 1 divided by r x x 0. So, therefore, your optimal prediction, that is x hat of n, this is simply r x x 1 divided by r x x 0 into, this is essentially your first order autoregressor. This is essentially your first order AR1 model, that is your x hat n equals r x x 1 divided by r x x 0 times x n minus 1. And now one can ask, what is the modeling error or what is the regression error? This is essentially your r x x 0 minus a 1 times r x x 1. Remember, this is your a 1 equals beta. So, this is going to be your r x x 0 minus r x x 1 divided by 0 times r x x 1, which is essentially equal to r x x 0 r square x x 1 divided by r x x 0. So, this is essentially your regression error. This is essentially your regression error, okay, for this first order AR model. Alright. So, essentially that completes our discussion of the AR modeling, that is auto-regression, which is a special case of regression. Essentially we are trying to regress using the past samples of the same process, and we are using the property that these samples are wide and stationary, right. So, essentially the correlation, that is what we call as the ACF function, that depends only on the lag, that is the expected value of xn minus 1 or xn minus I into xn minus j is r xx I minus j. Alright. So, that completes this discussion, which I have already said is very important, as many applications in forecasting, coding, compression, etc. So, please take a look at this. Again we will come back, we will continue our discussion of other similar concepts in the subsequent modules. Thank you very much.